You sit down at a desk, place your plotter across an aeronautical chart, and draw a perfectly straight line towards your destination. The map dictates that your intended ground track, your true course, is exactly 090 degrees, due east. But when you climb into the cockpit and turn the aircraft to match, the magnetic compass on your dashboard doesn't read 090. If you steer by that plotted number exactly, you will veer miles off your intended route. This happens because the paper map, the Earth's magnetic field, and the metal frame of the aircraft all disagree on the exact physical location of north. The first discrepancy is variation. The geographic North Pole, true north, is the physical axis where the Earth rotates. However, the Earth's molten core creates a magnetic North Pole that sits hundreds of miles away. Variation is simply the angular difference between these two physical locations. The second error is deviation. An aircraft is built out of metal components and packed with electrical wiring, alternators, and radios. These systems generate their own localized magnetic fields. These internal fields push and pull on the compass needle, dragging it away from magnetic north. This presentation slide defines a third factor, magnetic dip. Earth's magnetic field lines do not run perfectly parallel to the surface. As you move outward from the equator toward the poles, these invisible lines curve and dive vertically into the ground. Looking at this schematic of a direct reading compass, we see how engineers compensate for dip. The internal float and pivot assembly is pendulous, meaning the center of gravity hangs below the pivot. This prevents the compass card from jamming as it tries to point downward, but hanging freely means it will swing due to inertia, introducing kinetic errors anytime the aircraft accelerates or turns. The Earth causes variation, the aircraft causes deviation, and the mechanical design used to fight magnetic dip introduces maneuvering errors in flight. To navigate accurately, you have to convert your mapped true course into a flyable compass heading. The standard calculation sequence is true, variation, magnetic, deviation, compass. You can memorize this progression with the phrase, "television makes dull children." When calculating down this chain, from a paper chart to the cockpit instrument, we follow a strict mathematical rule. Westerly errors are added, and easterly errors are subtracted. A common memory aid for this direction is west is best, east is least. Let's apply this to a planned flight. Your chart shows a true course of 135 degrees. The local variation is 5 degrees west. Moving down the chain, we add west. 135 plus 5 equals a magnetic heading of 140. Inside the aircraft, your specific deviation is 2 degrees east on this heading. We subtract east. 140 minus 2 leaves a final compass heading of 138 degrees. To fly exactly 135 degrees over the ground, the pilot must steer 138 degrees on the compass. In the cockpit, you often need to do the exact opposite. If ATC asks for your true heading, you have to calculate upward from your compass back to the map. When you move up the TVMDC chain, every mathematical rule inverts. You must now subtract west and add east. If you are flying a compass heading of 275 degrees and your deviation card reads 3 degrees west, you subtract that west value. 275 minus 3 gives a magnetic heading of 272. If the chart variation is 10 degrees east, you add that east value. 272 plus 10 reveals your true heading is exactly 282 degrees. Calculating from the instrument back to the map requires flipping the math. Applying the standard west is best rule while moving up the chain will compound your errors and ruin the calculation. The DGCA CPL exam tests these concepts by burying the data in specific terminology. A dashed line on a chart connecting points of equal variation is an isogonic line. A line connecting points of equal magnetic dip is an isoclinic line. The exam heavily tests the kinetic errors caused by the pendulous compass design. In the northern hemisphere, acceleration creates a false turn to the north, and deceleration shows a false turn to the south, remembered as ANS. When turning, the compass lags behind north and leads south, remembered as UNOS, undershoot north, overshoot south. The trap occurs when a question places your aircraft in a location like Sydney, Australia. In the southern hemisphere, the Earth's magnetic flux lines pull the needle in the opposite direction, meaning every kinetic rule inverts. Ans becomes sand, and unos becomes onus. Finally, watch for questions regarding extreme latitudes. Because magnetic dip is 0 at the magnetic equator, the compass sits perfectly level and those kinetic errors disappear. That if you fly directly over the magnetic poles, the dip angle hits 90 degrees. The needle tries to point straight into the floor, rendering the compass useless. Acronyms will cause you to fail if they don't match the environment. Always verify the latitude and the hemisphere before applying a rule to an exam scenario. True to compass goes down the chain. West is best, east is least. Variation comes from the Earth. Deviation comes from the aircraft. You can lock in these conversion rules by practicing the specific trap questions available in our testing platform. Accurately correcting for magnetic forces is the baseline for all flight planning. Once you can consistently calculate the exact heading to steer, you have the mathematical foundation required to execute dead reckoning and intercept VOR radio radials.